Okay, dear everyone, I think I can welcome you to this. I think it's the third lecture of a webinar in the series of dynamic calculation methods for building energy performance assessment arranged by Dynastee and all of us partners. So my name is Peder Bacher. I'm from DTU in Denmark, and after me, I will give 1 hour of lecture and or like webinar, and then Iriati will give 1 hour after me today. All right, so I hope you're all well. You cannot interrupt me while I'm speaking, so I hope my sound is fine and that it works out. And you can check your sound by going up to this in the Cisco WebEx thing running on your computer now. And if you don't hear me, you need to change your audio setting. But I think you have tried this these days so many times with the online meetings, so I hope it works for you. If you have questions during the webinar today, then you need to write that in the Q&A box. And we will not today have interaction, but we will collect the questions, and then we will next week go through the questions and have and discuss them with you. All right. Yeah. So it's stated here that we'll gather the questions and then we will do a discussion and next Wednesday. Right. So what we're gonna work with today is, or what I'm gonna present to you is, or I'll try to introduce you to statistical modeling of dynamical systems. So I don't know your background, but I think it can be very varying, but I'll try to take it as if you had some engineering background and you do have had some course on statistics, but now let's see how we can use the statistical modeling techniques for dynamical systems and time series analysis. That's what we call it. So these are the different points we'll go through, but let's just jump right into it. So what are we working with? We have data and from some system, and we want to use the statistical modeling techniques. I hope you see my mouse. I don't know if I have to put some. Yeah, I think you see my mouse cursor. Yes. Thank you. So basically what we do is what we call statistical inference, and that's actually basically extracting information and drawing conclusions from data. And in that process, I just like this quote a lot. We should try to make everything as simple as possible, but not simpler. I think it's a quote from Einstein. But the point being, if you have a too simple model, then it's not going to be the best model. If you have a too complicated model, it's not going to be the best model. So the question is, which model should we actually use and how complex should it be? And that, when we're working with data and statistics, then we let that depend on the data we have. So ultimately, when we have some data, we will actually select the model we will use based on this data. The statistical techniques we have, we can estimate model parameters and we can estimate their uncertainties. That's what we know, already. We can estimate some parameters based on the data. And of course, statistics, that's like we have the privilege of also knowing how accurate we know these parameters. And then the next thing that is really important is that we have techniques and where we can calculate mathematically, you can say, and we have ways to verify and argue that we found the best model. Or rather, we could say that there is not one best model, we know that. But using these techniques, what we can do is we can find what we call a suitable model. We'll come back to that, which is really the model that we should use given this data. So not too simple and not too complex model. Yeah, so what we can do when we use these techniques, we can extract information, draw conclusions from data, and of course we can use these models for prediction and use them in applications where we do control. So we do some kind of optimization and operate some system based on this. So what's this is what we call time series analysis. When the data we're modeling, when it comes from time series, which is data sampled over time, and often what we have to do is that we have to include the dynamics of a system. So we're modeling dynamical systems. We'll come back to what that means in particular. But we call it time series analysis, and that's a lot of literature from way back in time. And actually, this is still what we're very much using today in many applications. I mean, from medicine to robots to finance, this is used everywhere. Yeah. But of course, computers evolved since then. So but much of the modeling techniques we're using are actually, discovered, let's say, in the 60s, 70s, and we're basically building on that all the time. But of course, a lot of stuff has come too with all the modern, let's call it, machine learning techniques. So, but when we talk about time series analysis, let's try to generalize models into 3 different categories or types of models. This is a kind of a simplification, but just to get an overview. So the first type of model is what we would call a static model. So it would not include a description of the dynamics of the system. The next type of models are discrete time models based on transfer functions. We will call those RMAX models. And the final type of models that we will use are called Graybox models. And they can be formulated in continuous time. And that's why we can really combine the physics and statistics. So basically, we use differential equations, so taken directly from physics, and then we call them stochastic. They become stochastic differential equations once we write them up in the way such that we can use them for doing statistics, or doing inference, statistical inference. So I'll go through these 3 types of models, and they can all be tweaked in different ways. So even though these RMAX models are linear models for linear time invariant systems, then they can be tweaked to become a nonlinear in many ways. But we'll try to take it from scratch and see how these models are actually formulated and how they work. So to explain it a little bit more in detail, let's try to do it like this. If we have a static model, we will basically think of this. We have some measurements. So some measurements we want to basically predict. It could be the heat load of a building or the temperature in a building. Then we have some inputs, which could be the ambient temperature, solar radiation. And then the model is some function of these inputs. And eventually we have an error term because the function of the inputs is not exactly equal to the measurements. There's an error. And that's very important in the statistical model. That's actually what makes it a statistical model, that there is an error in the model. So that would be the static model, where we basically don't describe the dynamics of the system. If we then go to the next type of model, the next one we could say would be an ARX model, an autoregressive with exogenous input model. And the difference to the linear regression model or the static model would be that instead of just a function here of the inputs, we would have what we call a transfer function. We'll look at how such one works later. And then the next step is to actually say, okay, there's an error in this model, but it's just, let's say, instantaneous in time. But if we extend this model, we can actually extend it to what we call an RMAX model. So it gets an moving average term, which is actually a transfer function of the error, which is abstract and hard to understand, but it makes sense once you start working with it, that you want to include that in many applications. And finally, the Graybox models, they are actually state space models, either discrete or continuous. We will think of them as continuous, but they can easily be discrete models. But yeah, what happens here is that you have a set of system equations, usually continuous time stochastic differential equations. Don't get confused about, oh, like it sounds very exotic, stochastic differential equations, but we can actually work with them quite easily once we have software for doing so. But it's a state space model, so we formulate basically a set of differential equations describing how the states of the model, so representing the system, how it evolves over time. That's what we have up here in the system equation. We also have here a function describing how the error evolves over time. The error is going through the system. It gets a little bit exotic, but most of the time we don't do much with this, but we can actually do quite advanced things with this system error part of the model. And then that was the system equations, the states, and then we have measurement equations where we would have the measurements that we want to predict. Again, indoor temperature, heat, or something from a building within the building applications. And then the measurement equations are formulated by a function of the states and the inputs. So how the measurements were taken as a function of the states. Sometimes it's just one of the states that are directly the measurement. Sometimes it's a function of the states. And we also have a function describing how the measurement error, how we model the measurement error. Usually it's just a normal distributed, random variable. Okay, so that was sort of the three types of models. And what's important here is that in all these models, there's a description of the error. So in the model, we have to say how the error, let's say, behaves. And actually, we describe those as they have to have a distribution, a probability distribution, because we don't know the error, but we say it will have certain distribution. And that's what makes it a statistical model. Versus what we could call here a white box model, where we would not have the error. So we would deterministically predict how the system would evolve in time. But here we say, in the stochastic models, we say we know the system will evolve in this way, but we also know that the error evolves in a certain way. And that's what allows us to actually basically do all the statistics. Yes. So we will go through these three types of model with some examples, so it hopefully makes sense in more detail. So let's start out with a very simple model, a linear regression model. That's what I kind of assume that you all know from basic statistics course in engineering, that you have some output variable y, and then you have a linear function of an input variable x, and you have the error epsilon here. And they are, when we formulate time series models, we always use the t. So we say at time t we have an observations of the y, and we have a value for the t and for the error, for the x and for the error at time t. So you just quickly to remind you of this model, it would be a linear regression model. So you would have x here on the x-axis and y on the y-axis, and if we just think of it, normally we would have some values here, not in time, but just some values, and then we would fit this regression, and we would fit this linear model line, so it's just a line basically, and where it's 0, that's where you have this beta 0, the intercept, and here when you have a the slope, the other parameters, the slope of this line. So if you go 1 on x, it increases, y increases beta 1. And what we can do when we have data, so we have the data, the points here, we can actually find the line that fits the best by doing this least squares, find the line that minimizes the least squares errors. And then, so what we have done when we have done that is that we have found the estimates of our parameters, then we put a hat on them, and then we have estimated the line based on the data, or that's our estimates. So that's what happens here, is that now we have the data, and now we have calculated the estimates of our parameters in the model. And once we've done that, if we have some XY data, what we need to do is to check our assumptions. We have certain assumptions behind this model. So what we will do is that we'll take this part over here, which we will call the prediction. And if we subtract the observation minus the prediction, then we have what we call the residual. So it's an observation of the error. So and then we will check if these residuals are actually living up to our assumptions behind this model before we can trust the parameters and the estimates of uncertainty and all that statistics. And so this we would call the residual. So it's an observation minus the prediction of the model. And now we will investigate if the residuals lives up to the two assumptions we have behind this regression model. And the first one is that the error is normal distributed. So we say that the error follows a normal distribution with mean 0 and some variance. This normal distribution is less important if we have many observations. Then we don't need to be that worried about that the error is normal distributed. The second assumption behind this model is that the error is independent identically distributed, which means that the errors are not depending on other variables that we have, or any of the variables we have, and that it's not dependent over time, so it's not dependent of some previous value of the error. When we have time series, that's very important for us to check to understand if we have modeled the system correctly or as good as we can. I mean, these two assumptions are there. Because they have, if we are to trust the statistical results, so basically that the estimates of our parameters are unbiased, and that the uncertainty estimates are also good, then we have to check these assumptions. We also do this in order to develop the model, because often we can, by checking the residuals, so basically we take the observation minus the prediction, and if there's something that our model did not predict very well, then we can see a pattern in the residuals, and then we can learn how to improve the model. So that's what we do all the time. We fit some model, and then we check the residuals, and then we check validate if the model is fine or we actually need to improve it. So let's try to do that with some simple example. But first of all, we need to know what white noise is. And now I can ask you, but I cannot hear your answer. But we need to know what white noise is and what the autocorrelation function is. So I'll quickly go through those first. So basically, the autocorrelation function is a function which checks for autocorrelation for correlation in time, so correlation between lagged values of a time series. So basically, so we see the result of the autocorrelation function here for some data which I just generated. Let's just go and do this. Actually, you can do it here. And now I just open R, and R Studio. It's just an editor for R, so we can generate some. This is just random distributed values. So 141 random distributed values independent of each other, normal distributed. So we can plot that over time. So we can see here we just get some noise basically. If we then calculate the autocorrelation function of this, so it's the yeah, there's a function in R for calculating this. It's called ACF. So we just feed the values to this function. Then we get this this result. And what happens is that this bar here, yeah, we can't see the x-axis here right now somehow. It's called the lags are on the x-axis. So this bar here is the correlation between the values of x and the series lagged shifted one step. So we basically see if there are any systematic pattern in time from this result. We see if there's a correlation between the value and the previous value here, and if there's a correlation between the value and the previous value 2 steps behind here. And in this case, with these independent random numbers, we don't see any significant pattern here. And all the correlations are more or less below these blue lines, which is at 95% confidence interval. So we would expect every 20 of these to stick out of this, and that's more or less what we have here when we generated these random numbers. So, okay, that worked nice. We generate some normal distributed noise. So actually, this is the type of result we want. Our residuals should look like this if our model is good, right? So let's try to generate some other type of time series. So I did that here. I took some of this white noise and I put it through a low pass filter, basically generating some dependency of the previous values. And now we see that result, there is clearly a pattern here. So if we just take those values and plot them, that's this plot, and then calculate the autocorrelation, then we see here a clear pattern in the autocorrelation. And we see now what we will say is that this series is not white noise. That's what we can conclude from this result of the autocorrelation function, where we have clearly a lot of these bars sticking out of the 95% confidence interval. So we'll say we can reject the hypothesis that this is white noise. So it's something else, and basically we need to do something if we want to model this. We need a model. Yes, so we fit the model and then we analyze the residuals, and if they are not white noise, then we can still improve the model. That's pretty much sort of the basic technique that we use. Let's try to do this in a setting where it's actually related to a building. Let's just think of the most simplest building and model we can think of. Let's have this building here. That's a very simple building. And let's model let's say we want to model the indoor temperature, the indoor air temperature here. And let's say that we will use in the model the ambient temperature or external temperature. And let's say the model is very simple. We'll just represent the envelope of the building with a resistance and the thermal capacity of the building with a capacitor. And let's say that the external temperature is actually what drives the system. So it's actually just a equivalent then to a voltage source. So this is what we call an RC diagram, which is like a way to illustrate a electrical circuit, but it's equivalent to the models we use for a thermal thermal system. This is the simplest model we can come up with. It just has a resistance and a capacitor, and it's driven by some voltage source, or temperature source, which is the external temperature. It's just changing, and then the internal temperature is changing as a function of the external temperature. And here we have the ground. So let's play around with this model, the simplest model we can come up with, and see how it will work out when we generate data with this, and we actually estimate these type of time series models with this data. So let's work with that. Let's say the TE is the external temperature and TI is the internal temperature, and we have those values at time 1, 2, up to n, so we have n observations. Now, let's only have the external temperature, and let's use this ODE, ordinary differential equation model, which is modeling this system. So we say that the differential is equal to, the difference 1 over RC times the difference of the internal and external temperature. And let's solve this model ahead in time. So the black line here is the external temperature driving the system, and then we will have the red line here, which that will be the internal temperature. Okay, so we can see when the external temperature goes up, the internal temperature goes up, but sort of a little bit delayed, because it's actually entering the heat will need to flow from the external temperature into the state of the house, or like the internal, and then the internal temperature will increase. But there are dynamics in this system. Yes. So let's add a bit of measurement noise, then statistical models work better. So we say that when we measure this internal temperature, we have a bit of noise just from the electronics in the sensor or something. So now we simulate this system, and let's try to use that data and fit some models. Let's try first with the simple linear regression model. So we will say this is just a linear regression model, and it's not describing the dynamics. We could call it a static model. What will happen is that we say to the model, estimate the parameters. So estimate this omega, which is like the beta 1, the parameter of the slope between the external temperature and the internal temperature. And basically what this model will tell us is that it will give this blue line as a prediction. So it means basically that it says that the internal temperature will just be immediately responding to the external temperature. So our model will predict this blue line, but in reality we have, or simulated, the data that we're trying to predict is the red line. So what we're going to do is that we're going to subtract these two from each other, and then we will have the what we call the residuals, and they look like this. So now we want to check if they are independent and identically distributed. So basically that means, is there a pattern in time between the lagged values of this time series? All right, we can already see there is a pattern, but let's use the autocorrelation function to get a more, let's say, statistical results. So we can see there's a pattern. If we calculate the autocorrelation function, it looks like this, and we can clearly see this is basically a test if the residuals are independent of each other in time. And we see, no, they're not. Too many of these lines are sticking out of the blue confidence interval, so we can reject the hypothesis that this is white noise. It's not. So we need to do something to find a better model. Then we ask ourselves, what can we do? Okay, let's think about it from physics. Now we actually know the system is working like this. So what if we solve this in time? Yes, then we have this solution that the internal temperature will evolve in time. If we know the internal temperature at time t, and we know how the external temperature will evolve over time, then we can solve this and know the internal temperature ahead in time. This is the solution to this first order differential equation. All right, let's have a look at that. What can we do? Yeah, let's say that delta t is 1. So there's one time unit between the sampling times where we observe this system. And let's say that t is constant between the sample points. Then the solution looks like this. Or we rearranged it a bit. So that at some point ahead in time, one step ahead in time from the current position, we will have this solution. Okay, and this one is exponential to 1 over RC. Oh, that's actually a constant. R and C are constant for this system, and this term is also this factor is also a coefficient is also a constant. So basically, and we actually know that this is a value between 0 and 1. So basically, we can write it like this, taking this part as phi 1 and this part as omega 1. And they're both between 0 and 1. Actually, one is 1 minus the other, but let's just think of it as two parameters. And what we can do now is actually this is actually what we call an ARX model. So the value one step ahead in time is a function of the current value times some coefficient plus the input value times some coefficient plus the error. Then it's an ARX model. We basically just add this error or noise term, and then we have what we call an ARX model. And yeah, we can shift that in time. So we say the observation we have at now is a function of the previous time step. Okay, so this is actually, if we look at this, oops, that's actually just, that we can actually formulate, that's just a linear regression model. In this way, formulated in this way, this is just, we have this value, the previous observation of TI, and the previous observation of TE. So we can just fit this using the linear regression techniques for estimating the parameters. So if we do that, ARX models can just be fitted using least squares regression. So it will just give us very easily these parameter values given the data. And then the model will predict this blue line. So we can already see it's much better than the previous model predictions. It's very close to the red line. And let's then, of course, examine the residuals. And here we have the residuals. So yeah, we subtract the prediction minus the observation. And then we do a bit of juggling around here. We'll come back to that. But these are the residuals, and they do look like white noise. Let's use the autocorrelation function to check. They look like white noise. There is something here because there is actually, this bar here is sticking a little bit too much out of this confidence interval. And actually in this little bit artificial setting, what happens is that we actually miss the MA part of the model. And so we can add that. And basically it means that we will now, we add what we call a transfer function of the residual. So basically we use also, the model also includes a lagged value of a term which is formed by the lagged value of the residual. So the last residual we had also enters the model. And if we do that and fit this model and predict and do predictions, then we get this very nice blue line where we've actually filtered out this noise we added. And now if we examine the residuals, then we can see, yes, these are what we would say, they are white noise residual. They are white noise, this time series of the residuals from this model. And yes, one of these are sticking out, but if we look at 20, that's okay. 1 out of 20 is sticking out. In reality, you often have a few sticking out, but they are not very high. And then you say, this is actually fine. This is a good model. So now we can validate that this model is actually the best model we can, yeah, it's a good model for this data. Yeah. I'm talking a lot. Normally, I would probably ask if someone had a question, so I would interrupt me. But yeah, in this format, it's not really possible. So I'm just gonna keep on going, and hopefully it's video recorded, so you can go back and see if there are some details that it was too fast or something. Okay, but one thing that we should notice here is that what we're doing is that we are validating the one-step predictions, residuals. So that's basically what our model formulated, was that it said the observations, okay, now it's written at time t+1, or we can shift the time step, but it's basically saying the observation at t minus minus the prediction of the model given, the time step before, given the previous time step. So this is a notation we use. The prediction with a hat over the output variable at time t, given data or given information up to time t minus 1. That's the residuals that we are analyzing. That's basically how our models are formulated. They do a one-step prediction and are fitted to that. And then if they are white noise, this basically says, at least if things are linear and time invariant, then we have the best model we can come up with. Given that it's not a too complicated model, which will still produce white noise, but will not be optimal once we use it for prediction and so forth. But we'll come back to that. But this is a technique that we will use when we do time series analysis, the basic techniques to fit the model and analyze the residuals, and then try to evolve the model into a good model. Usually starting with a very simple model and then adding terms to the model, parts to the model, until we have these white noise. So what we saw here was that let's make this into, let's look at these different categories of these classical linear time series models. The AR autoregressive model of order 1 looks like this. So it's just taking the previous value of the output times some coefficient. So it's not having any input variables. If we then call it an ARX model, then it has an input exogenous input variable. So it could have an X as input, which then gets a coefficient, but the same structure, just adding this input to the model. If we then extend it to an R-max model, where we add the MA, the moving average part, then we add this lag of the previous residual of the error, the previous error, and basically now we have a transfer function of our errors on our errors. And what this means is that basically in all systems that we sample in the real world, there will be uncertainty even on the X and the inputs and other things that affect the system. And once you have uncertainty or noise going through the system, so if you have some building and you have some stuff that's you don't measure correctly the ambient temperature or the external temperature, and so you have noise on that, then it actually this noise also needs to be filtered by the system in order to have the best model. So that's why you have a transfer function on the error. So most of the time we really need that part in the model, but also many times we can live with this model because it actually works well for prediction and stuff. Yeah, and then we have the assumptions of our errors here, that it's normal distributed and IID, independent identically distributed. Yes, which we check with the autocorrelation function. So we could write X or U as the input. It's just some variable, and of course we can have multiple inputs and multiple outputs of the models. Now this was models of order 1, so they would only include one lag. We can formulate models up to order P, so we would include lag 1, lag 2, up to lag P in the model. And basically, we can come back to what that means. It means that they are equivalent to a system which has basically, if you think of RC systems, if you have two RCs connected in serial, you can think of it like that, then you would need a second order model. So you need like 2 in the model. If you have more, then you would need up to P, let's say RC parts in this model, then you would need a model of order P. And we can formulate all of them up to order P. Same assumption, of course. We don't need the same order of these AR and XM and MA parts. We can have different. Here it's just formulated with that they have the same order. all of them. So that's, let's say, classical time series analysis models. And if you take time series analysis 1 course, the first course we have at DTU, that's basically the models you work with. Oh, they are extended in the end, but this is the, let's say, classical time series analysis models. Yeah, and we can formulate those completely generalized by saying that these, instead of writing it out with the lags, then these are actually formulated as what we call a polynomial of order p, and then it's this b is this backshift operator. So it's the same as writing this one up here. It's just formulated as one function or polynomial operator. And then we can formulate it like this, and this also, yeah, you can look at the slides afterwards. This also, by doing that, then we can see when we talk what is a transfer function. A transfer function is actually, when we formulate it like this, that the current value of the output is the input through this transfer function. So and up here we have the polynomial for x, and here we have the AR polynomial. And these, when you divide these two, this is what we call a transfer function, which we usually write with an h. And once back in the days when you're designing electrical circuits, you would work a lot with transfer function. You would go to the frequency domain and add together different parts, and then go back to the time domain, and then you can calculate how things would work out in time in say an easy way. But it's the same type of models that we can now estimate the parameters in using the statistical methods. Right. So we can fit, if we want to fit the ARX models to the one without the MA part, we can just use LM or linear regression. It's just a linear regression model, so it's a closed form optimization. We just multiply some matrices. We always get the let's say optimal parameters, the least squares parameters. We get in R, we can use this LM function, and in Python, other packages, other languages, there are other functions. The ARMA model in R can be fitted with this ARIMA function, which is already in R, in the base R. And the RMAX models, there actually we need some other packages. We can use this MARIMA package, but there are other packages which allows us to also have the MA part in the model. And these are linear models, so linear discrete models, they will work perfect if you have a linear time invariant system, if that's what you're modeling. So it's a linear system, linear in the inputs and the lag values, and it's not changing over time. Then you can use these models, and they are the best models. But they can also be tweaked in many ways, such that the model can be used for modeling nonlinear systems. But we'll not cover that here, but that's from here you can use many techniques to tweak these to make them fit also nonlinear, include nonlinear effects in the models. Very well. So now I spent most of the time, but now we enter the last type of models, which are the Graybox models, and how to use this. I will demonstrate this with the software that we have had at DTU for many years, CTSM-R. It's a package in R, so I'll show you how that works. Probably I was speaking too much, and it's too much information in too little time, but yeah, that's how it is. So the CTSM-R package is continuous time stochastic modeling in R. And okay, one could say that it should be continuous discrete models because we actually have discrete data, and that's actually continuous discrete models in a sense. Let's look at how they are. So why do we call them Graybox models? Well, that kind of makes sense if we think of it in this way. A white box model, we would generally think of something that was a model that was formulated using only prior knowledge from physics. So usually when simulating a building, you would say it's composed like this and this, and now the heat or temperatures will evolve like this over time. But it doesn't include any let's say, noise terms or error terms in the model. On the other hand, we would have a black box model, which is like, we don't know how the physics work. We just formulate a model and it works for prediction, but we cannot interpret the parameters directly as physical variables. In between, we have the Graybox models where we formulate the models as physical models from physics, and we estimate the parameters directly to the data. And we can understand using physics what is the meaning of this value. For example, thermal resistance. We estimate directly the thermal resistance. So yeah, we have the package. There's a website here where you can find different material, and there's documentation and some examples if you want to get started. And yeah, CTSM-R. So the web page was ctsm.info, so you can have a look at that. But I'll try to demonstrate how it works. So when we have to write it up in a beautiful way using math, then we write it up like this. It's a state space model where the x is a state vector, and how it evolves over time is described by this part we call the drift term. So basically a differential equation is a function of, yeah, what are the states now, and the input, some input variables, and time. It can be a time varying system, and more. And then we have this next part, which we call the drift term, which describes how the error evolves over time. Usually this is quite simple, just one value times this Brownian motion process. Don't think too much about this, but in the beginning, but what you see is that, okay, we have actually, let's say, noise entering through the system, described like this, that the noise enters directly into the states of the system. And then we have the discrete time measurement equation, which says how were the measurements, the kth measurements, so yeah, at time tk, how was the measurement taken as a function of the states and inputs, and we also have the measurement error. So we can basically formulate up here using physics some differential equations, and down here how the observations were taken as a function of those states and the model. And basically that forms the model. So if we're to do that with this simplest model that we're working with, the RC model, then it looks like this, and we will just write that directly into the model here. In the system equation, we'll say it has one state, the internal temperature, and it has the drift term here, which is directly this model we know from physics, 1 over RC, and the input minus the current state. So it's just a differential equation. We put it directly here, and then we say there's a diffusion term. Okay, it's just a value, some coefficient times this Brownian motion, or we will estimate this value, and we do understand something from it, but not that much in the beginning. Let's just introduce it like that. And then we formulate the measurement equation. Okay, in this case, we simply take the state, which is predicted using this model. Then we just take that state and say that's actually what we measure. So it's a very simple function. It's just one-to-one. The state is what we observe. And then we add a measurement error. And that together forms the Graybox model that we will now use and fit to the data. Yeah, there's one little detail, is that in this current setting, this model we cannot separate the R and the C. That's impossible. So we will just basically, instead of RC, we will actually say this is a linear model, and R times C is what we call the time constant. So the model that will fit is just 1 over the time constant. So we cannot get R and C separated here in this setting, but we can estimate the time constant and then fit the model, which is, yeah, equivalent to the R-max model, as we'll see. But now we'll fit this model to data, and using the package, we will simply define a model, and we will write in directly the differential equations, and so the drift term and the diffusion term. We'll write that in. We'll say which are the inputs, how is the observation equation, and a parameter describing the variance. So yeah, just to say that it's really nice to write in these models in this using this package, because we just directly write the differential equations basically and how the model is set up. And then for the estimation, this is now a heuristic optimization. So it's not just some matrices we multiply together and get the parameters all the time, optimal parameters. We'll have to do some optimization, and we need to tell in the package the optimizer there. We can use other optimizers, but the built-in optimizer needs a lower and upper bound for each parameter and an initial starting value. So we have to put that to some reasonable values, and then we can run give the data, which is now in a table basically, and run this function on the model, and then we get our results. And basically when we do that, and then we calculate again the one-step predictions, and we run the autocorrelation function on those from this Graybox model fitted to the data we had from our the data that we generate ourselves from this very system. We use the same model, and voila, it works very nicely. We get actually the result that we get is very, very close to the RMAX model that we fitted. So we can see here turquoise and a blue line, and green and blue line, and they are very, very close. So it's some numerical differences basically, because the model is the same, continuous time and the discrete time model. And we can also, the residuals are very close. They're a little bit different, but that's due to some numerical basically differences when we fit the models. But the models are the same or equivalent, basically. Yeah, so what did we do here? And I know this is probably too much information right now, but I just continue, and I have 7 minutes more, so we'll just go ahead full speed. So in this example, we had a model with two parameters. Okay. Sorry, I'm jumping a bit, so I'll skip a bit this. But what we're using for estimating the parameters in these Graybox models is what we call likelihood theory, maximum likelihood, and it basically means that given a model and given a set of data, then we find the parameters which maximize what is called the likelihood function. So I mean, you can look up that, and there are many books on that, and it's like somehow the most beautiful statistical method, because you can basically fit any model to data. Once you have defined your model with a description of the error, then you can formulate the likelihood function, and you can maximize it and find the best values of the parameters and get all the statistics out. But anyway, I won't go into details on that, but I'll just tell you that it's maximum likelihood that we're using, and you can take courses just on maximum likelihood. It's used in many different types of models. Now we just use it for stochastic systems, or like dynamical models, Graybox models. So basically, we formulate this maximum likelihood function and find the parameters which maximize the likelihood function. In reality, we minimize the negative log likelihood function and so forth, but that's numerical reasons for that, and you can all look up to that. This is just something that is very broadly used in statistics, so we just use it here for these Graybox models. Yes. So I'll skip this actually, but then I will say that what's running under the hood, which does this, is what is the Kalman filter. And the Kalman filter, I don't know if you have been in contact with it, but it's a very beautiful, let's say model. And basically, you know, linear regression is least squares for a regression model. Basically, the Kalman filter is the least square, is equivalent least squares estimation of the states in a system as it evolves over time and you have data. It's actually calculating least squares estimates of the states. So in a setting where you have a dynamical model, or actually a linear, depends. But I mean, that's a Kalman filter. And you can spend years on understanding how it works, and I'm not fully there, even me, but I can use it at least when it's implemented, and then it works very nicely. So yeah, look up the comma filter and do that many times, and then in different settings you will get a hang of it, and maybe try to implement it yourself, which is not that difficult actually. Yes, so that's used a lot. So basically, but let's go through the steps. When we want to do this Graybox model, we'll load some data, we'll define a model, we'll define the initial values and parameter bounds, then we'll run an optimizer. So the common filter we will at given some parameter values in the model, then the common filter will be used to calculate the likelihood of these values. So we will set some parameter, initial parameter values, then we will run the common filter, and then we'll get the likelihood, and then you'll use an optimizer to change the values of the parameters, and then we will find, using this optimizer, the parameters which maximize the likelihood function or minimize the negative log likelihood function. Yeah, and basically once we've done that, then we need to check the result. The optimizer, since it's a heuristic optimization, it can fail, but it gives us indications if it has failed. And afterwards, we can look at the estimated parameter values and the statistics of those, and we can look at the residuals and analyze the results there. And yeah, now I think I simply ran out of time, but there is an example, and we'll distribute the code and these examples. I'll just show that we'll put a zip file with the code and these examples, and basically we will it shows the example of fitting these models to a building and running different models and running estimating the parameters and analyzing results, and then developing because now the challenge, once you're able to estimate the model and do the predictions and calculate the residuals. Now the challenge is to find out which model should you use. And that's basically the hardest problem of all this, because you don't want, I don't know if you know this, but it's called model complexity variance. The balance between bias and variance of a model. So if we have some model and we actually use this model for predicting our data, then if we have a given set of data, then the blue line here, the turquoise line, is actually what's going to happen if we fit a model and we just add more complexity to the model. What will happen is that when we train this to some data set, then it will just perform better and better and better. The more stuff we add to the model, it will just always get a little bit better. But that's a problem, because if we just keep on doing that, we will have a much too complicated model, and it's not going to be the best model. So what we need to do, actually, there are different techniques, but we need one way of seeing that is to say we fit the model on some training data, and then we actually do the prediction and on a test data. And what will happen is that as we increase the complexity, the model is getting better, but at some point, the prediction, we will overfit the model to the training data. And when we do that, then the prediction error on the test sample, on the test data, will actually start increasing. And now what we want to find is this point where it starts to become worse at predicting on the test data. So that's a bias variance trade-off. We want to find this point, and we can do that in different ways. We can either use statistical tests for model selection, where we start with a simple model, we make more and more complicated model, and then we actually test if the more complicated model is actually improving enough. We can look at the blue line here, and we ask the question, is the model improving enough as we add complexity? And we can have a statistical test for for calculating if the improvement was significant. Or we can simply add some penalty for model complexity. So that's when you use ARC or BIC information criteria. Or we can do cross-validation, where we actually, when we do the parameter estimation, we do train on some data and test, let's say, during the training, we test on some other data, and then we do that a lot. And then we can find the best model for prediction using cross-validation. So that's 3 different techniques we can use. But you can look into that. And the best model is sort of always a compromise between this. It's not too complex, it's not overfitted, it's not too simple, it's not underfitted. And we can use these different techniques and we can start with a simple model and add complexity. We can start with a complicated model and remove complexity. Yeah, so that's called model selection techniques. So you can look up that. So, and if you want to do these Graybox models, you can have a look at this website. We also have a more intense, let's say, summer school where we actually work on, where we have different exercises and on this, and also, of course, on courses on DTU. Yeah, so that was it for my part. That was more or less exactly an hour. So I hope it made sense, and I know I probably was speaking too fast and jumping through a lot of stuff, skipping details and important details and stuff like that. But it gave you an overview, and that's what I could do in 1 hour. So now Irati will present an example of using the Graybox models for different applications related to buildings. And thanks for now, and I will hand over the screen and microphone to Irati, and I hope you're fine, and then I hope we can do some discussion next week on these topics. And we'll send out the code behind this and the example I did not make to show afterwards and put it on the website. All right.